So let me start off by saying welcome again, everyone, to another Mathematic virtual program. I'm Rachel Robinson, Vice President of Mathematic, and we are absolutely thrilled to have you joining us for another fantastic webinar. So let me start off by saying thank you to Vision Elements for putting this together. Obviously, AI and medical imaging is something that is top of mind for a lot of companies, and specifically when it comes to artificial intelligence, right? The buzzwords are all there. So what does that really mean? What are the practical applications for this? So I'm excited to hear what Hila has to say about all of this. So I am going to say we have Q&A at the bottom of the screen. Please feel free to type your questions in there. That'll be the easiest place for us to take a look at them throughout and at the end of the presentation. We absolutely encourage the questions, so please do that. And if you have any technical issues or anything else, feel free to shoot me a note in the chat. And with that, I will turn things over to Hila.
Thank you, Rachel. Thank you. I'm very happy to be here. So hi, everyone. My name is Hila, and I'm a computer vision and AI researcher and associate at Vision Elements. And today, I would like to talk about how to use AI in medical imaging. So first of all, who we are a group of PhDs and masters in science and engineering. We have decades of computer vision and artificial intelligence accumulated experience, and we are based both in Israel and in the US. Among our clients, we have large enterprises like Medtronic and Philips and Samsung, and also small companies and startups. We do various projects in all kinds of sectors. We have projects in retail application, in gesture recognition and 3D reconstruction, and tracking, among other, through autonomous aircrafts. What are we going to talk about today? So today I'm going to talk about how AI advances the medical imaging in healthcare. What are the data challenges and annotation consideration we should take into account once we initiate an AI application, what algorithmic approaches to consider and how to address it, whether we can use some other type of additional data and how to incorporate it, and specifically how to incorporate the time dependency. This is a last subject only if time will allow. So AI has revolutionized the healthcare industry in the past decade. And I think that one of the main reasons for that is its ability to learn any kind of task once it's giving the right data, of course, with the optimized learning algorithm and algorithmic approach. And it can achieve that task with high accuracy, and sometimes even more than a human can, specifically for tumor detection and MRI slides, abnormalities in the eyeball, border of an organ, and COVID areas, inflammation in the lungs, and so on, and much more many tasks. Actually, whichever task people dream of, given the right data and the right algorithm, it can achieve high accuracy result. And I think this is what is really amazing about it. So what are the use cases that are being used today in the healthcare domain? So I think this is a very interesting case right here. I'll just move this over here. I think it's going to be good. So, in this case, for example, the use case that is described in this image is the use of AI as a preliminary diagnostic tool where it enables an early stages of abnormalities detections. Like in this picture here, in this breast tumor, you can see here that an AI was able to alert for this kind of tumor in this kind of size, this kind of abnormality, which, I mean, to me at least, it seems very the same as the environment. And later on, only 4 years after, and a human could actually diagnose this. So I think that the AI has a very great impact on preliminary diagnostic, and moreover, because it's fast and doesn't require any human intervention, it can also be very fast and be used as a fast screening tool in the clinical process of the diagnostic. process. It can also use as a monitoring treatment tool. Like if a physician prescribes some kind of a treatment to a patient, and then the patient can go through a series of imaging, and the AI can monitor the treatment, whether that organ reacts good and well to the treatment or the tumor, and so on. Some AI applications are now being developed to be incorporated within the image acquisition phase. Same as we can see here, that the main idea here is to use the AI technique to enhance the image, and therefore to be able to use, for example, in CT acquisition, to use less radiation. That will also reduce the cost for the actual process and scanner itself, but also will benefit the patient with its well-being, reducing the amount of radiation or the current in the MRI scan, and so on. Other AI application is for robotic navigation, where basically the robot itself will be able to perform remote surgeries, where the robot will be able to input will have to input the images from the cameras or from the sensors, and then to process it with the AI, and then to react accordingly, and to remove the tissue, or to perform and to, of course, navigate to the accurate location that it needs to be, and so on. So what enable all this great use cases and science? So I think that most of the people within the AI domain will agree with me, is that having the right data for your need probably is the most important thing. So here, for example, just move it up here. So what I mean by the right data is, I think mainly to use first, let's say this is the first requirements, is to use the same data that you are training your AI or your model with in the test time. So whatever data you're going to use during when the application will be tested or will be used, the same data needs to be included within the training. Because here, for example, we can see two types of X-rays. Okay, one has, for example, a wider vertebra in this X-ray of the spine, and here it's much darker. We can see that this has some margins that doesn't appear here, and other lighting conditions that are different, and so on. So we have to take into account within the AI application that we're going to use, whether if we wanted to include these two forms of X-rays, for example, then we would want our data to include all kind of varieties that we wanted to be able to work on. So for example, if we wanted to be able to detect vertebrae in this X-ray, and we wanted to be able to detect the vertebra in this kind of image and both in this kind of X-ray, then we need to include both of them within our training set. And with having that said, it means that we need to check all kind of factors within our data, like what are the camera angles? I mean, if we're referring to AP view or lateral view, what is the lighting condition that the images are taken at? And we need to have it the same both for the test data.
Hila, sorry, I wonder if everybody can still hear you. Have a look. Something happened to the audio on your side. Now it's okay. Can you speak a little bit?
Hila, I would suggest turning off your video. Perhaps it's a bandwidth issue. If you turn off your video, perhaps audio will come back. The other option is to jump off very quickly and jump back on. So audience, can you hear Millie and myself? If anyone could just pop in a message into the chat, just to, okay, so they can hear us. Great. Okay, thanks, you hear all wonderful. Thank you. So, okay, we lost Hila. So, Hila, I would suggest jumping off perhaps and jumping back on very quickly. It should be no problem to do that if you would like to try that option. Perfect.
Okay. I can say in the meantime that we got several questions, which is great. Since they are mainly professional questions, Hila will be with you as soon as she's back, and once the presentation is over, we will try to do our best and answer as many questions as possible. And you guys rock, because the questions are really interesting. Thank you.
Thanks everyone for your patience. We've all been on Zoom for, I don't know, a year and a half now, and we still have so many issues. It's crazy.
No, but I think that it's really perfect. I mean, things happen, and Hila, just unmute.
Yeah, can you hear me now?
You're back. Absolutely. Okay, great.
Yeah.
Thank you. I'm sorry. I don't know what happened. Okay.
Totally fine. Nothing happened.
Sorry. So I think so. I don't know where should I go back to? Because I don't know what was like.
No, just the next slide.
This one, okay. So I hope everyone can hear me now. Now, if there is, so because I'm sharing, I'm not always able to figure it out if you guys can hear me or not. So just raise a hand or wave or I don't know, whatever. So anyway, so what I was saying is that I think that the most important factor to take into account is to have the similar imaging characteristic between the test data that the AI application is gonna run on, like what data is going to be used when the AI application would be used, and what data, and to have the same characteristic of the data during the training. And that refers to camera angles, whether, for example, in this Xray, it's taken from the AP view or lateral view. And if we want to use them both, then we would have to consider either train one network that will include all views that we would like to consider, or train different network for each type of view. We would also have to take into account the lighting condition, whether, as you can see this here it's darker, here it's brighter, and so on. What kind of imaging type, if we want to train for multiple modalities, if it's CT or X-ray or MRI, or we might consider to do a different network for each type of modality. What type of target is being recorded in the image? If it's if it's a liver tissue that we want the AI to work on, then we should train on liver tissue images and not breast tissue images. Okay, that's the concept. Indoor and outdoor is less common within the healthcare domain, but might be also applicable whenever they decide to do MRI scans outside. And in any case, we would want to have, if we want the AI to treat all kind of conditions and all kind of data modalities, we would need to have as much as large diversity in the data as we can. And for the balance factor, that's also something we want to consider, and I will elaborate about that in the next slide. And for the question of how much data we need, so I think the best answer is as much as we can get, and I will elaborate about that issue a little bit later as well. Okay, so after we have discussed a little bit about what data is the right for application, we also need to consider other data challenges that we need to take into account. And I think in the healthcare domain, the most important one is the small amount of data available. It's because of the data privacy issue and confidentiality issue of the patients. So there aren't as many public databases available as we have, for example, in ImageNet or COCO, where we have millions of images and annotation. So here, the public one are usually very, very small, and even if they're not public, and we do somehow gain some data. So it's, from this hospital or this client, a little bit of that, and it's not in the millions like we have in like a different domain, and that is an issue that needs to be addressed. And I think that some of it is addressed by the FDA today, that there are some legalization initiatives to be able to create large database that will be able to be shared to advance the research in the healthcare domain. Specifically, when we develop the application, we can consider, in this case where we have small amount of data, to use a technique called transfer learning, where the idea in the transfer learning is to basically take the model that we chose that is the best fit for our application, and to train it on a large database, let's say like ImageNet, that has millions of images with annotation on a different test, okay, like completely different data, completely different test, and then use that model and the knowledge that it gained, and then retrain it with a fine tuning on our small data set. And I know it sounds a little bit weird that, how would training on natural images would help me detect vertebra and X-ray. But there is some what is called common features that the network and the model learns to extract and use that can be used as a retrain. Another issue to consider is that sometimes, even if we do find some public data set, it doesn't necessarily always have the right annotation that fits to what we are trying to achieve. And that can also be addressed using all kind of semi-supervised and unsupervised techniques that allow us to use small data set with annotation that we can handily mark them and whatnot, and the other database would be unannotated, or with the completely unsupervised technique, not using annotation at all. And as I mentioned before, there is the non-balanced data issue that in this case, we have, especially in the healthcare domain, we have a lot of in a lot of the cases imbalance between the different classes of the data. For example, if we would want to classify someone that has a condition or someone that is healthy, for example, so we might suffer in our data from imbalance between those classes, because in like a normal or ideal world, we would want to have the same amount of data for people who are healthy and the same amount of data people who have some type of a condition. But in reality, because of how rare the condition might be in the population, then so this would also reflect in our data, for example. Also, if there is some type of medical imaging process that is taken at the end of a clinical process, then it might be that most of the patient that will get to the point where their image is taken might more likely be medically ill versus healthy ones, for example. So we won't have as much as healthy subject in this case. Also, if we have most of our data taken from facilities in North America and in Europe, so we would have underrepresented racial group like from South America or from Asia and so on. For example, in this case, when we have unbalanced data between the classes, we can use techniques that once we would train the network, once we would train it to reach the goal that we are trying to achieve, we would train it in a way that will take into account this unbalanced situation. We will teach it to ignore, like to try to balance between those classes. For example, with a type of weight loss that will give more weight to very small group of classes, for example. And another consideration that we might take into account is, for example, creation of artificial data. For example, we could use other models like guns to create healthy subject to balance the healthy versus medically ill and so on. And to the million-dollar question, what is the minimum amount of data needed for the network to be generalized and robust and to work well? So I think that the main two factors that needs to be addressed here and need to be taken into account is the model complexity. And of course, so that's the first one. And the second is the nature of the problem. So, and about that model complexity, we know that as the model getting deeper, we need more data for it to be robust and to be able to have high accuracy results. And we can see here, for example, that the more the model is more deeper, then additional data here can help improve the actual score on the test set. Because here, for example, we can see a comparison between different models, the simple unit with ResNet, unit with DenseNet, and unit with Inception Res V2, I believe, sorry. And we can see that even, for example, for the simple unit, which is a more shallow model versus the others, additional 600 or 700 images didn't improve that much of the result, for example, versus the DenseNet 121. So there is a tight connection between the model complexity and its ability to learn given more data. On the other hand, another consideration we need to take into account is the nature of the problem. I mean, if it's a very difficult task, a task that will be difficult to separate between objects, or there is some kind of overlap or occlusion, so that would be a more difficult problem in case of segmentation, for example, versus if we're talking about one label classification, that might be a simpler problem. So that also has an impact of how much data will we need. And another two things that I wanted to mention in this regard is that especially as I said before, in medical healthcare and in medical imaging, using transfer learning that I mentioned before, training on a large database and retraining on our small database usually gives very good results. Which allows us to actually incorporate AI within the healthcare. So that's also a good thing to remember. And also with the use of active learning, which is a type of a semi-supervised technique, allows us to actually choose the most suitable and beneficial subset within the data that would benefit our model the most. It's like it enables us to select the most beneficial or challenging images or data set from our old data set, that we can use that and almost only that to improve our model. And this can also allows us to support a small data set that needs to be annotated, for example. So after we have talked about what is the importance of the data and what are the challenges that we have within the data and the annotation that we need to consider, now I'd like to talk about the different algorithmic approaches and what we should consider in this case. So the algorithmic approaches to consider depend on the task we're trying to achieve and the data and annotation available to us. So for example, if we would want to train a model that wants to do segmentation, for example, to segment the vertebra and the spine. So we can decide first whether we would want to do a binary segmentation that just segment the vertebra from the background, which has two labels, whether we want to do a multi-label segmentation, if we want to have many labels, for example, to label each vertebra separately, for example, whether we whether we are dealing with three-dimensional or two-dimensional segmentation. So that actually is referring to when we have, for example, a CT cube that is a volume. So the question is whether if we do need to do segmentation, should we choose 3D segmentation or 2D segmentation for each of the slides? If we're talking about regression, Should we choose a model to output points in the image based on points of interest that we're interested in, or should we use some kind of a bounding box algorithm, like to just confine some kind of a box within an object we would like to detect? That's also based on regression. If we want to do classification, should it be a single label for the whole image or volume, or multi-label? If we're using multiple networks, should it be cascade, like in double unit, 2 units one after the other, or parallel? So now I'm gonna share with you some of our experience with recent projects that we worked recently, and how we approach to each of the projects, and which algorithmic approach to choose from. So here, in this case, we wanted to extract so here, first of all, we can see X-ray of the spine. We wanted to extract the femoral head's center and radius for each of the femoral in the X-ray, and we could do this in 2 ways. One of them would to train an AI that is based on a regression model that would be expected to predict 6 numbers, X, Y location for each of the femoral head, so X and Y, and the radius, so 6 parameters overall, and that will need to train a regression network that for each input, that each X-ray input would output 6 numbers, X, Y location of the center, X, Y locations of the center, and the radius. And a second approach would be to train a segmentation network. That the idea here in the segmentation network would be to classify each pixel in the image, whether it's background or foreground, where the foreground is what is labeled here in pink is the femoral head area. And after we will be able to achieve this, we can do some computation and extract the center and the radius. And we have tried both, as I think often the case in AI, because of the different data and different tasks. It's not that there isn't always one clear answer for all. And what we have found out that the results of the segmentation approach in this case gave better accuracy. And we believe that this comes from mainly 2 reasons. The first one is that by definition, the segmentation problem is more confined, since each pixel is given 2 choices to be marked as 0 or 1. So the optimization of the learning process of the model is more confined. And then it is likely to converge better. The second reason is that in this regression approach and model, the model was trained to predict 6 numbers that has range of numbers that can be predicted, and 4 of the numbers can actually be seen from the image, can be directly extracted from the image because they're the center of the femoral heads. But the radius, for example, is not something that directly can be extracted from the image, since it is calculated. So that might also pose some limitation or some challenge to the network. In this case, for example, we wanted to segment the 3D CT volume of the spine. So the CT volume is basically a cube that has an XY spatial resolution and also a Z resolution. And what we wanted to achieve here is we wanted to segment each vertebra to be segmented and extracted from the background and from the other bones in the CT, but also to be separated from each other, because we also wanted to know which vertebra we are referring to. So we needed to be separated, whether it's L5, L4, L3, and so on. And here we needed to consider whether it would be most beneficial to do a 3D segmentation, which means that we would segment the entire volume, where each voxel in the volume will be given a label, either 0 or 1 in this case, or whether we should choose a 2D segmentation approach, where we would basically crop the CT for each of the 2D slices and train the network to segment the each 2D slice separately. And I will show you. I'm sorry about that. 1 second, I know I can't. Sorry, I'm trying to. Okay, I'm sorry about that. Okay. Yeah, I'm sorry. So I'll move this farther here. Oh, that would be better. Okay. So so here, for example, we can see how a 2D slice of that CT spine volume looks like. And we can see here, it's very clear that the ability to separate the different vertebra within the 2D slide is more complicated. You can see here in yellow, one vertebra, and purple, the other vertebra, and you see how they are interlaced and integrated together. So for example, if we were to choose a 2D segmentation approach, in this case, the model would have a more challenging task to train for, because it's more difficult to separate the vertebra in this 2D slice versus we see the whole complicated 3D model. So in this case, and specifically if there are any kind of deformities like frictions and other deformities that would also make this situation even more complicated. Another thing or issue to consider is how to incorporate this 3D volume, because we're talking about 3D volume of data and 3D kernels of the model. It needs very large computational resources, and we cannot feed the network with the entire volume of the CT. So we would need, for example, to crop patches that would need to fed into the model. Now we would need to consider what type of patch size or what type of volume we would need to feed the network, because we would need to be able to include the entire vertebra. We would need to fit the actual 3D model that we're trying to segment into the volume size. So that's also another thing to consider. I mean, if it would only fit in half, that might have been an issue. We wouldn't be able to segment it. And as I mentioned before, the computational resource available to us. So in case of 3D, we need to take into account that, as I said, it's 3D kernels and it's a volume. So we would need a large memory. The GPU would need to have large memory enough to be able to contain all of this. Our batch size is going to be smaller than in case of the 2D, and this might also impact the stability of the training process. And of course, our training, because it's so heavy, might take longer. So it's also issues we need to consider. Okay, so for example, in this case, if we would, let's say, instead of wanting to segment each vertebra, we would just want to label the CT volume, whether it's normal or abnormal. So in this case, we would want to consider a classification approach. Now, what we need to consider here as well is whether, if we want to label the entire CT volume, should we, in this case, use 2D slices, and for each 2D slice, label them whether they're normal or abnormal, or should we use volume patches, or should we use the entire volume? So in this case, because the abnormality is so local, like we can see here and here versus the whole spine, so it would be, if we were to take the approach of using 2D slices or crop patches, we were likely to have most of them within the spine to be normal. And then we would need to make some kind of other mechanism to decide what is the label of the entire spine. So for example, in this case, what would be most reasonable to do is to use the entire volume, but to downsample it, because this is a very simple problem of one label classification, and the abnormalities are very local. So we want to have the whole CT volume to be able, so the model would be able to look at the whole CT volume and to extract the correct label. So basically, you can see it depends on the task we're trying to achieve. What is the data that we have? What is the illness or medical condition we're trying to detect? Here, for example, so this is a different algorithm. This is here we train a regression network to detect 4 landmark within each vertebra in the X-ray. So the idea here is that we wanted to do some kind of alignment between the CT and the X-ray. So it was sufficient for us for this alignment only to detect or to extract these 4 points within each vertebra. So we trained a regression network that its target was to predict for each vertebra the 4 points of its corners. Now, you can see that this model is, of course, less informative than a segmentation approach. If we would want to consider to do a segmentation on this X-ray, but it also requires less effort in annotation, for example, if we don't have any labeling. So the annotation here can be very, very quick, and the model can be trained even with less data and more quickly. So it basically depends what you're trying to achieve. Here, we just wanted to achieve 4 corners landmarks within the vertebra. So after I have described with details what are the algorithmic approaches to consider and what is and how should we address to each approach, now I want to talk about what to do in case we have and what kind of additional types of data can we use. So here, the idea is that to always look for additional information that might improve the accuracy of the AI model that we are trying to train. So for example, in this case, in this project, we can see a segmentation of subtree in a coronary angiogram. So this is a coronary angiogram of the coronary vessels in the heart, and this is a subtree that is segmented out of the entire coronary vessel tree. And the idea is, what other information can we use to better improve this AI application? And if there is an additional data that can be used to improve it, how can we incorporate it? So for example, if we would know to have some kind of a heartbeat cycle estimation, we could maybe use this information to select a single frame within a dicom that the vessels are more filled with blood, you know, that of course the blood contracts and expands. So we would maybe want to pick the frames that the subtree and the vessels are more expanded, contain more blood, more spread out. For example, that would be an easier image or task for the model, for example. Maybe we would want to use all the frames within the dicom, and we would want to exploit somehow the time dependency within them, because the heart cycle has a defined cycle. It contracts and expands, contracts and expands. Maybe we could use that information to understand, to make the task for the network easier by the ability for it to understand that this is the exact subtree that we want to extract in each of the frames. So, and if we are using all that frames, then we might also want to use other information within the DICOM, like what is the frame rate that the DICOM was taken, what is the heartbeat cycle can also be used in that to try to also add information about the cycle of the heart, even given all that video, for example. We might also want to consider if we have different views of the same patient, because sometimes, for example, we're not sure from a single view if the vessels are crossover, overlap, and if we would look at the same subtree from a different view, it will be more, it will be much clearer, because the vessels from a different view might be, if it's a crossover, it might be within a certain gap from each other. So all this information can be incorporated and should be, if exists, into the AI model to make the AI model results more accurate and more robust. Then in this case, if we do have all this kind of information, how can we incorporate it within the training? So if we're talking about additional images, we might want to add those as another input channel. Or we might want to, within the same input metrics that we're feeding into the model, we might want to add it as a second input. We would have two inputs of images, for example. If we have a series of images, we might want to consider multiple frames layer, like LSTM, some kind of an RNN that enables to process multiple frames on the same time. And if we want to, let's say, combine numerical information in addition to the images, like I mentioned here, the heartbeat estimation or the frame rate, then we might want to have, we might want to combine it in the feature space, where we would have one path that extract all the features from the image itself, and a second path that will use that numerical information, and then they will be combined within the latent space, the feature space, to a signal vector, for example. So throughout this presentation, we have encountered many use cases of AI in the medical imaging. And when mapping out a process for initiating an AI application, in most of the cases, there isn't one truth that fits it all. And this is, I think, that we have discussed about this subject. And I think what's mainly important is to first define the goal that we are trying to achieve when designing the AI application, and what information we are trying to gain from it, and then consider the data challenges that arises, what is the data that we have, what are the annotations that are available to us, and then to choose what algorithm or what concept should we choose. And these choices are dependent on each other and have a great impact on the final model performance. Thank you very much, and stay safe.
Hi everyone, Hila, thank you so much. I think it was fascinating, and every time I kind of think, how come I didn't choose to work on these topics? It's excellent. We have a lot of questions. We will try to take one or two questions, and I'm going to share via the chat both Hila and my email, and you guys can approach us anytime if we don't manage to answer your question, okay? I think some of the things that Hila, some of the questions were already answered, but I'll go through them. My name is Mili, by the way. So we have a couple of questions from Stephen. What imaging modality was used in the breast image? Which imaging modality?
Okay, I don't know why I can't see the. Okay, maybe I don't know why I can't see the questions, but okay.
I'll explain.
Okay, so in that image, oh, sorry, I don't know why I can't have my mouse. I'm sorry about that. So I think, so this was taken from a website by Daniela. I think this is the one that he's referring to. And I think that this is an X-ray image, but I can double check. I don't know if that answered the question. Okay.
Okay, and we had another question from Stephen, just a moment. How does spatial resolution impact the AI process? And also the same question for the signal to noise ratios.
So again, I mean, I don't know why I can't see the questions. Can you please repeat?
Yeah, so how does the spatial resolution impact the AI processes? Okay, and the same question goes for the signal to noise ratios.
Okay, so for the spatial resolution, so I think that the most important thing is that the feature that you're trying to, or the task you're trying to achieve should be detectable within the exact spatial resolution that you currently have in your data. And I also think that it's very important to unify all the data as pre-processing step before you start a training. So if you have several modalities, or if you have several resources of images, they should be within the same spatial resolution before you start a training. But I think it is important to make sure that the spatial resolution that you're using will allow for the object that you're trying to detect, or the abnormalities you're trying to detect, or the task you're trying to fulfill. I hope that answers the question. And regarding the SNR, so the SNR, I mean, that's I think a great question. We also have encountered a problem where you have a very low SNR images, then the level of accuracy of the model train decreases. And I have seen some research about first enhancing the images, and then as a pre-processing step, if possible, or with a different network, and maybe train them together. And this is what I meant when I meant like a cascade network, for example, where you first enhance the data, and then you can use a second network to achieve the task or the goal that you're looking to achieve. I hope this answered the question.
Yeah, cool. So one more question, Hila. You were asked by someone called Kirsty. You say to train with as much data as you can. Can you speak toward biased or over-fitted algorithms? I don't know if you covered that already, but perhaps you want to say a couple of words about it?
Okay, can you please repeat, Millie, again? I'm
Sure.
sorry.
No worries. So Kirsty wrote, you say to train with as much data as you can. Can you speak toward what's like the biased or overfitted algorithms?
Oh, okay.
So the question is about, the biased, what happens if the data is biased or overfitted?
Yeah, so I mean, I'm not sure that if this is what you were referring to, if there is a case where you have too much data, that would probably cause and like overfitting of the model. So from my experience, as long as you keep a separate set for training and a separate set for testing and validation, then from my experience, even if you add more data than what you need, it likely not to improve the results, but I don't think, I mean, I didn't see it causing any bias or any overfitting on the validation and test it. It just won't improve the model. But maybe there are cases that this is the different situation.
Okay, I think, Rachel, if that's okay with you, we will take one or two more questions and then we'll ramp up. And we really encourage all of you. I see that there's a lot of sun here. I'm located in Israel. We are located in Israel, and it's afternoon. The sun comes right here. So please feel free to also speak with us afterwards. Okay, we would really love to help you, both on technical professional questions and on business-related questions. So just one or two more. Someone called Lydia asked, I would like to understand the level of cleaning and adoption of AI-based device. How much data needs to be collected to prove reliability and credibility? I think you touched based on that, Hila, but I don't know if you want to say one more thing about it.
Yeah, I did. So I mentioned it earlier that this is, I think, the big question, because it basically depends on the task that you're trying to achieve. Because as I said before, if it's a simpler task, then you might need less data. What model are you using? If the model is very complex and deep, you would need more data. But I think that if you use, as I mentioned, the transfer learning technique, for example, you can get good results even with a couple of hundreds of images. Again, don't take this, I mean, it depends on the task and what type of modality and all, but even what I was trying to emphasize is that even if you use transfer learning, even with small amount of data, you can achieve good results.
Yeah, okay. Okay, one more. We have a lot more, but I'm really sorry about that. So what techniques do you use to account for small data sets in early medical research? Could you hear me, Hila?
Yes. So as I just mentioned, I mean, we always, when we consider medical imaging application, we always use transfer learning, usually from ImageNet, because we found it very beneficial. We sometimes, as I said, try to use this as a new technique, the active learning, for choosing the subset that we are trying to annotate, for example, because we do use annotation. I mean, we do invest time to annotate our data, and I think it's also beneficial. I mean, there is some benefit to use unsupervised techniques, but I think that it's worth in general to annotate at least some of the data. But I think mainly what I would start at the beginning would to use the technique of the transfer learning. That's for sure. I mean, and large databases, ImageNet, for sure. If there's a different one that has millions of data that more fitting to your task. I mean, not even the thousands, millions. That's I think the best approach to start.
Okay, excellent. Thank you very much, Hila.
Thank you both so much. Yeah, this has been a very informative. Obviously, it's a huge topic. We could probably talk for another 2 hours on this. Maybe we'll have to do a follow-up. But as Millie and Hila said, please feel free to reach out with our contact information to answer any questions that didn't get answered. We'll also make sure they get the transcript of the Q&A so that they can reach out to you if they didn't get a chance to answer your question as well. But thank you all again for sticking with us.
We apologize for any questions. I won't sleep tonight because I'll feel really bad if we didn't manage to answer. But you do have the emails, Millie at Vision Elements or Hila at Vision Elements, and feel free to approach us. We would love to get in touch and to hear from you.
Definitely.
All right, everyone. Have a wonderful rest of your day. Bye.
Thank you very much. Thank you, Hila. Bye.